So yes, now with no more delay, we have Pantelis Samartidis, sorry, from MRC-BSU that will talk about this nice interesting topic. So you're welcome.
Thank you very much for the introduction. Thank you all for coming. I hope I can give a nice talk, one that you find interesting. So just to say that I don't have too many slides, so please feel free to stop me at any point if you have a question. I don't mind that at all. So this is some applied work of mine that I've done with several colleagues that I will list in the end. And I guess the best way to start speaking about it is to, give you some background about the example. So this one goes back to the days when, COVID was on the rise, and the NHS was trying, to find ways to somehow contain the pandemic or at least minimize the damage done. And one of the ways in which they try to do it is the so-called NHS test and trace. So this is a program that has multiple functionalities, but I think the one that you are most familiar with is the contact tracing. So imagine I give a PCR test somewhere and goes to the lab and I test positive for COVID. So what would happen back on the day is that my details would go to a central hub of NHS test and trace, and then they would try to get in touch with me. And they want to do that for two reasons. So the first reason is that I might not be aware that I'm infected. So they really want to let me know that you have this virus and you need to stay at home. Actually, it's your legal obligation to stay at home so you don't spread the virus further. And the second thing they did is they asked the people who were positive, and I will call these people the cases from now on, to give them a list of contacts. So this is people who they had been in physical proximity with. And of course, you want to do that because you want to, let the contacts know that they might be in risk. So they should be aware that, they are in risk of this. And yeah, early studies, and not just from the UK, but also from around the world, showed that contact tracing was actually a very important, tool that we had to, sort of contain the pandemic. It did a good job. Like there were studies that found some positive results in that sense. And for that reason, the NHS tried to make it even more effective. So starting from July 2020, they introduced an intervention, the so-called local tracing partnerships. I will abbreviate that as LTPs for the remaining of the talk. And the purpose of these LTPs was to assist the national grid in, executing the contact tracing properly. So when the national test and trace did not manage to get in touch with an individual, the people in the LTPs who were working locally, they would use their intelligence about the region, and they would try to do the job themselves, where the NHS failed. So the task that we had in this example over here was to evaluate whether or not the LTPs were actually effective in improving contact tracing. And I will say in a bit about what I mean effectiveness. So the main challenge here is that this was an observational study. So who got the local tracing partnerships and at what time they got it was not randomized in any way. It depended on the interest, the resources that the local regions had to implement this intervention. And so we need to be very careful when doing this evaluation because there might be some the usual problems that are associated with observational studies. This is a high-level summary of our data set. So I just have to say that the period that this study covers is from the 1st of July 2020 to mid-November. This is around the time that we started working on this project. And we have data on roughly 200 spatial units. Most of these units are UTLAs, upper tier local regions in England. And down here, you see two characteristics of the data set. So on the left-hand side, I'm showing you, like for each day during the study period, how many of my spatial units had the intervention. You can see that at the beginning, nobody had it. But as we gradually moved towards the end of our study, more and more areas started the local tracing partnership. So it's what you sometimes find in the literature being referred to as staggered adoption of the treatment, of the intervention. And the other important characteristic that I want to highlight is that, the contact tracing is all about, getting in touch with cases. So I wanted to plot how many cases we had for each region and for each day of the study. So the x-axis over here is the date, and the y-axis represents the different spatial units. And you can see that at the beginning of the study, like the number of cases is very low. It was summer back then, so the virus was not spreading too fast. But as we go towards the end, the number of cases start to increase. And here I've split the panels between units that are never treated and the units that got an LTP eventually at some point during the study. And you already can see that there is a bit of a difference. Like these appear to be units that have quite a bigger number of cases, and that can mean many things. So I said we want to see if the LTPs change the effectiveness of contact tracing. So I now need to define what I mean by effectiveness. And in this study, we have 4 different outcomes. So this is the number of cases for each day in each unit. And we are interested in the following 4 outcomes. So the first one is what percentage of these cases is completed. In other words, how many of these individuals did we manage to get in touch with and complete the process. The second one is how many of the ones that we completed, we managed to do so very early, like within 48 hours, because of course it's important to do the contact tracing, but if you do it 3 weeks after, then the individual might have already gone and spread the virus, and that is no good. And finally, the other 2 outcomes are related to the contacts that we managed to elicit from the cases. So the third one is just simply the number of contacts. The more contacts we elicit, the merrier we are, because we can potentially protect more people. And finally, because we then also try to get in touch with these contacts, let them know, we count the percentage of them that have been successfully traced afterwards. So these are the 4 outcomes on which I try to assess the intervention. And yeah, I'll also put a plot.
What does completed mean?
Completed means that you've managed to have communication with the individual. So for a case, the tracing is completed. If, say, I give you a call, you pick up, I let you know that you have your infection, and you give me a list of contacts. You might have no contacts, but at least I need to get in touch with you. And for the contacts, it's the same. Like completed is when we manage to get in touch with these people. So again, this is just a plot of the data, the 4 outcomes, so percentage completed, percentage completed timely, log number of contacts elicited, and now percentage of contacts completed. So you can see it's quite messy. There's no clear indication of whether or not the LTPs have been successful or not. So just to say that perhaps this is the motivating problem for this project, but I want to say that it falls in a setting that we very much encounter in many applications in our work at the MRC Biostatistics unit. So when we carry out evaluations, typically they will fall into a setting that fits these 4 characteristics. So the first characteristic is that we have multiple units. So some of them will be treated, some of them will be untreated, but for the rest of the talk, I assume that there is at least one untreated unit. And sometimes we refer to these units as control units because they don't receive the intervention at any period during the study. And so apart from that, we also have the requirement that for each one of these units, we don't observe the outcome or the outcomes of interest just once, but instead we have a time series over the study period. Yep. And typically in our applications, this is not going to be long time series. It's going to be time series that are relatively short. So we have to take that into account when we are, developing a methodology. And then these represent aggregate data. So I think you already understand what that means from the example I gave to you. It's not time series on individuals, but rather a summary over many individuals. So a unit could represent a hospital or a geographical region, but we very rarely have data on individuals. And finally, we have the requirement that the intervention is non-randomized. So I have listed a few examples that we have seen in our work. So except for COVID, we also have
I'm sorry, my question to I was just wondering if the LCP process also determines whether a contact becomes a direct positive test COVID. Like, does the LCP process actually determine, based on one person that was infected, how many people they contaminate from other contacts?
so they are treated separately. Like a contact is just an individual that is given to us by case. That individual might, have a positive test, but I think I'm not the expert here, but I think they treat it separately. Doing a check. If the individual had a positive test already, then I think they try to contact them. And if they manage to, they put a tick in both the case and the contact. But not 100% for sure of that because I have not worked with individual level data, but that's what I recall.
For your COVID, what is an untreated unit then? So you request no individuals in the geographical area have been infected?
They don't have access to an LTP. Like there's no LTP operating in their postcode.
All right, but maybe there's people in there that have been contacted in their office or in other geographical areas.
Yes, this is very likely. I mean, it doesn't make too much of a difference about the outcome. Perhaps it makes a difference about some sort of interference assumption that I'm making afterwards.
But we assume there is no.
Yeah. I'll get to that. But for this, we make this assumption. And so yeah, I have a few more examples. It's mainly from epidemiology and public health. I just want to say before I go and show how we're gonna go about modeling this thing and final stuff. Speaking that this is like a very large literature. The setting I showed you before, it seems quite restrictive, but actually it appears not only in public health and epidemiology, but there's also like applications in econometrics, political science, and marketing. And there are a lot of contributions from these areas, and more recently there are also contributions from the machine learning research. So the main methods that you might have heard and even use yourselves include differences, interrupted time series, synthetic controls, matrix completion, and then variants of those methods. So these are the main methods, and sometimes people combine them. As I say, it's a big field. It's growing very fast. Like you have methodological publications in the orders of hundreds every year, the last 3 or 4 years. So if you are interested in looking at, an introduction to the field, I suggest the YouTube lectures by Yiking Su, and I've also listed a few papers that have good literature review for you to look at. And then, of course, here I'm going to propose yet another method that can be used in this setting, and you might rightfully ask, why do you need to do that when there are so many methods already out there? And the answer is that our examples are quite specific in some sense. So the first of all, we are dealing with count outcomes. So I already showed you before in our application that we have 3 binomial outcomes and 1 count outcome. So despite there being quite a few methods, like not all of them are readily implemented for count outcomes. The second issue is that, as I said before, my time series are quite short, and I usually don't have too much data available. So I wanted to do something to, combine multiple outcomes affected by the intervention in order to, improve my statistical efficiency. And finally, our colleagues are typically interested in uncertainty quantification. Again, this is not very straightforward for all of these methods. For example, for static controls, there is like, I don't think there's a consensus of how inference should be done. And finally, we want something that can model effect heterogeneity. So once we go and estimate the effect of the intervention, we also want to see like what drives any possible heterogeneity in this effect. So I'll show you a method that we believe can accommodate those things quite well. And before going into the details, I just want to give you some intuition. So let's take the case completion as our motivating example. So here we have the study period, and we have a unit from the real data set, and we have on the y-axis the percentage of cases completed. So this probability, of course, we don't know exactly. We observe binomial data, but there is some uncertainty associated to it, to the true probability. And the key thing is to make the observation that we have data under 2 regimes. So the vertical line is where the LTP starts in that region. Before that, we have data under the untreated regime. So the intervention has not been affected yet. But after that, we have data under the treated regime. So the intervention has started to act. So my task becomes to sort of use the data that I have in the yellow untreated regime and try to impute something that you might have heard as the counterfactual. It's is the outcome that would have been observed in this period if there was no intervention. So say the unit did not introduce the intervention, what would be the trajectory of the percentage of completed cases? If I can find a way to do that, then the effect that the intervention had is just the difference between the two. So here you see that under the treated regime, the case completion is higher than what it would have been in the untreated regime, which means that the intervention is effective, right? So the question is, how do I, fill in this missing data here? And the answer is that I'll use the pre-treatment data, not just for this unit, but for all the units in the sample. And I'll try to make a model for this regime, extrapolate it in the post-intervention period for each unit, and calculate this difference. Yeah, I hope that makes sense. And one of the most popular methods to do that is the factor analysis model. So just want to go a bit into the details of this model. So it is a model that does regression adjustment. So regression adjustment is one of the most popular ways to deal with the problem of confounding and causal inference. So I have started with a vanilla model for continuous outcomes, and that's why I changed the notation to Y. And this model has 3 components. So the first one is the standard regression adjustment for confounding. You have some covariance xit for unit I at time t, and you say that the outcome in the untreated regime is a function of these covariance. Now, some of these covariance might be the confounders, and you really want to adjust of them to avoid having false inferences regarding the causal effect. You might be a bit concerned about the fact that I've just written that as a linear regression. You might think it's too simplistic, and you're right, but I think we understand the tools that allow us to relax the assumption of linearity very well. You can have something like nonlinear effects with spline, Gaussian processes, variable selection methods for when xit is high dimensional. So I'm just writing it there, but I don't think like that this is a serious limitation. You can change that very easily. The important thing about this model is that it also includes this product of terms lambda and f. From now on, I will call the terms lambda the loadings, and these are specific to each unit. And the term f is another vector. I will call the factors. And these are common to all units, but they are specific to each time point. And both of these vectors are unobserved. Yeah. So the idea is that because I have time series data, there is opportunity for me here to model an unobserved, contribution to the outcome. And in order to be able to estimate, to have a hope to estimate, I need to give it some structure. So because I have multiple time points per unit, I can estimate this vector for each unit. And because I have multiple units per time point, I can also estimate this factor. And so I fit this very simple model. We do it under the Bayesian paradigm. It gives us posterior distribution of all these parameters. Then using that, I can go to my treated units. I observe their covariates, which I assume are exogenous, so they're not affected by the intervention. I replace with my estimated values, and I get a projection like before. So this allows me to draw from the posterior predictive distribution of this untreated outcome. And this is how I'm going to estimate this effect. Then the rest I have observed, so I can just subtract one from another.
This is a bit like synthetic controls, right? So it's almost, or am I confused?
Yes, no, it is very much. In fact, I think like when they study synthetic control properties, they usually use
that's why you do a weighted combination of control units to, to construct and control each of them. Yeah.
Exactly. Yeah, there is an analogy. And for those of you who have used the latent factor model, it's essentially a model for the covariance matrix of time series. So I'm using linear relationship between the units to sort of project in the post-intervention period. The idea is very simple. So the key assumption here, the unconfounded assumption, there are many assumptions. No interference is one assumption that I will make, inconsistency, no treatment anticipation. I didn't want to list them in a formal mathematical way because that introduces a lot of notation. I'm giving a very good reference here. Like Pang and colleagues have made a very thorough derivation of where each one of these assumptions is needed. But the key unconfounded assumption is that once I adjust for the xi's and the lambdas, there is no more confounding of these effects. And so, yeah, as I said before, I cannot use this model for my own examples because I'm dealing with current data. And so what I'm going to do is adapt it a bit here. So here I said how we generalized it. And I have assumed that there are three outcomes, one of each type. So the model can accommodate normal outcomes, binomial and negative binomial outcomes. I'm assuming that there's one of each type, but this is not necessary yet. You can have multiple of each type, but to use the notation, I've just said, we have one of each type. So in the LTP application, we have three of those and one of those. And the idea is very simple. I think instead of having a factor model on a normal outcome, we have a factor model on each one of these outcomes. They have different regression coefficients, but the key thing is that all of them will share the vector of loadings here. As I said before, the reason that I'm struggling to fit this model is that my time series is too short sometimes. So if I have not enough data for one unit, if it has a small pre-intervention period, I have very little information to estimate its load. I'm trying to make use of the shared information between the outcomes to sort of improve statistical efficiency. And yeah, we can show in simulation studies that if you fit this model and there is indeed some shared variability, you get power. And if there is no shared variability, you don't lose much because the priors help us deal with this thing, as you will see in a bit. So all the parameters involved in this model, I will call for the remaining of the talk theta. Yeah, just letting you know because it will come up later. So this first model a multivariate factor model parameters I will call theta from now on.
So Pantelis, so you're not, I mean, by the fact that you've got the same loadings.
Yep.
But you're saying that F, G, and H could actually be completely different.
Yeah. Yeah.
So why does it intuitively make sense that you have the same loadings?
So one way to look at this loading is like as a vector of unit specific characteristics.
Okay.
So each unit will have some hidden characteristics. I cannot observe them. They remain constant over time, and they affect the outcome.
Right.
But the magnitude of the effect will change from outcome to outcome, right?
It doesn't matter that you parameterize it as lambda because of I, but not T, and F, T, but not I, T, right?
Yeah, it's one interpretation. Another interpretation is like, these are the factors are shocks to the environment, like to my system, like different shocks, and possibly different trends will affect different outcomes in different ways, but the effect, I'm assuming, remains the same. So there are two different interpretations depending on what literature you look at.
Are you implicitly imposing restriction and that F, G, and H are the same dimension?
I'll say in a bit, yeah. Yeah, I'll say in a bit. Hopefully, I'll be able to explain why this is not the case.
Okay.
As I said before, like I have, units on the y-axis, time points at the x-axis, and let's forget about the covariates for now. Yeah, let's assume they don't exist. I want to model a function of the expected value as the product of these two matrices. So this is lambda. The matrix that has rows to be the loadings of each unit. So here I have 4 factors, and then I have F, which has in dimension as many as the factors, and then as many as the time points. So it's a dimension reduction technique. Now the problem is I don't know how many of those I have, right? Both of these quantities are unobserved. It's very hard for me to have prior knowledge about how many of these I should expect. So how can I deal with that? And more importantly, deal with the uncertainty of this quantity. Yeah, this is one of the main things. So let's say that I started by saying that I have J star factors. That can be the maximum expected number of factors that you think are in the data, say 20 or 100. If you had a prior that could fill some of these columns with the true factors. So in the previous example, I had 4 factors. You see that this prior put them into the first, the last, and the 2 columns in between. You just set the remaining equal to 0. Then my problem is solved, right? Because this is very close to 0. Multiplied by the factors, there's no contribution. Only these 4 columns will have contribution. So I'm looking for a prior that is able to do this. And fortunately for us, this has already been done. So I've stolen this figure from one of these 2 papers. I think is the former one that I've taken it with. And we generally we take their approach to model the uncertainty in the number of columns. So we start by saying that the loading of unit I for the j factor. So this is now a scalar. Each unit will have a vector, but I'm talking about the scalar. It's coming from a normal distribution that has this phi parameter in the denominator of the variance. And then this is sort of something that controls the magnitude of this value. If this is very close to 0, then the scale of lambda becomes big. So it's allowed to take any values that the data might request. If this becomes very close to 1, 1 minus 1, it disappears. So the loading shrinks very close to 0. And then I have similar parameters for my columns. So not just the individual elements, for my columns. And finally, I have a global parameter that controls the amount of shrinkage in the entire matrix. Yeah. So the idea is that by doing that, I'm allowing both complete columns to be set to 0. They will be shrunk near 0, and hence their effect will disappear. And at the same time, I'm not shrinking the loadings that are within each column too much. This is something you don't want to do. If you want to interpret these things as latent characteristics, you might want to allow them to be different between treated and controlled units. You really don't want to impose too much shrinkage to them, because that's the whole point of this, that they might be different between treated and untreated. So this prior allows us to do that. And like Sam said before, it's not necessary that each one of these loadings will affect every outcome, right? So I want to be able to do something similar for the factors as well. So say I have a loading. The way we do that is by introducing these latent variables. I call them M. So in this example, I have a list of the loading. So the number was J star, and I'm showing the first 4. And I have 3 outcomes. So for each outcome, I'm choosing M to represent the one that is most affected by this load. Yeah. So in this case, the binomial outcome is mostly affected by this loading. I give that a variance 1 for the factor. So I will assume that the variance of this factor is going to be 1. And then for the remaining outcomes, I will leave the variance to be between 0 and 1. So it will be affected, the scale will be certainly be less on the binomial outcome, right? So if, say, loading J does not affect the normal outcome, then this variable can go very close to 0. Yeah, the value of the factor will diminish, so we have no contribution on that specific outcome. Now, one point is that for this work I have not assumed any temporal structure on the factors. Like that's a fair criticism, and the reason we haven't done it is because the computations become very, very hard once you do that. In some previous work we did, like we assumed that they have AR1 priors, so they have some structure over time, these factors. But it turned out that modeling this is not so important where are too many units. As I said, like when you have too many units, you can estimate the factor at each time point with good efficiency, right? So by not modeling the temporal aspect, you perhaps do not sacrifice much. But certainly when the complexity of the model increases and the number of units is very small, then this is something that we might want to consider in the future.
But when they hired these tracking trace people, I thought they just hired people off the street.
Sorry?
When they hired these tracking trace people, they just hired them off the street, sort of, right? So didn't they get better at tracking trace, like at the calling back or at the actual? Because like you had another example there with the hepatitis and stuff, right? Those are like the real expert tracking trace people that really could know how to call and
yeah,
and so maybe those are the local people that got hired afterwards. But initially, when they hired, they just hired anyone that wanted to work.
Yeah.
So you would assume that those guys, maybe they just crap and never got better, but you assume temporally they would actually get better at tracking.
Yeah, but we get there. We get there. I'll try to answer the question. Yeah, but there is some. I don't know how well I'm doing in terms of that. What is it?
Yes, you have everything.
Okay. So yeah, we want to like I will skip posterior computations in the interest of time. Just to say that this model is not so straightforward to do MCMC with, because there is the well-known non-identifiability problem, factor analysis. So you can, when I'm trying to calculate this expectation, this product, I can have an orthonormal matrix Q that multiplies lambda, multiplies F. The product will be the same, but the loadings of the factors will be different. So it's a well-known problem, and for that, the standard gradient-based methods did not work very well in our example, so we had to sort of employ something that used a variance covariance proposal that is specific to where you are. Happy to discuss that further, but I think that in the interest of time, I'll skip. So I'll just apply this method to my data set, and you see what's happening here. Like this is a scatter plot of the estimated, and I'm estimating by the posterior mean of all the effects that I had across units and across time. So say for day 29th of September, I had all these effects, and you can see that it is a big mess, right? Like there's just too much heterogeneity. I cannot say too many things. Like I can say that they're overall positive. Like most of them are positive. There is more mass above zero. So that indicates that the LTPs increased the case completion. But there's also like, quite some variability behind that. So this brings us to briefly speak about the second part of the talk. Is like whether or not I can make a story out of those. I sort of try to understand what is the thing that is driving this heterogeneity. And what you said is like a very fair point. When people start to work, then they don't know the work, or maybe they are random people now. As the local tracing partnership becomes more mature, then the results might get better. So for that, and for many other reasons, like in other examples, you can have questions as, what is the intensity of treatment? Like how many people should I put working into these local tracing partnerships in order to achieve a certain effect? Like how many resources should I allocate? Or if, I have multiple versions of the treatment, perhaps I want to ask which version of the treatment is more effective, right? So there are many reasons why we want to, model this heterogeneity effect. So one idea would be to take these point estimates and fit a model on those against some covariance. So how long has the unit has been in the intervention? I fit those. But this is not taking into account the uncertainty that is associated with these effects, right? So there is a bit of a problem there. So I'll try to do an alternative, which is to just model the heterogeneity. So here I'm introducing like this variable that is 1 if unit I is treated at time t. And if that's the case, then I will introduce this, what I call the heterogeneity model. So psi here is the effect that the intervention has on the log mean. Other than that, the model is the same as before. So for units that are not treated, this will disappear. The model will stay the same as before. But for those who are treated, you will have this. And here I put, 2 splines, one on the temporal trend. So I sort of want to estimate, an average effect that changes over time. And also what you mentioned, like the effect of, cumulative treatment time intervention plus some error. So I call phi the additional parameter. So there's the spline coefficients from these 2 functions and the normal error variance. I'll call them phi. This will become handy later. I'll fit this model to the data here. I'll try to see what happens. So the first thing I do is I compare the estimates I had previously in what I will call the unstructured model. So there's no model for the heterogeneity with the structured one. And you see what has happened here. Like, of course, on the left, I'm showing the posterior mean, comparing it to the 2 models. And I'm showing the credible interval width on the right-hand side. You see that I have really improved my credible interval width. This is expected because I'm using the treated data. But we can also see that by doing that, I have sort of, some of the effects that I estimated as very negative have now become very positive. So there's no very good agreement between the estimates of these effects between the 2 models. And there is a very simple explanation for that. So we go and check the output of the MCMC. So here I'm looking at, the last iteration. I'm looking at factor 12. And I'm looking at the values of the loadings between treated and control units. And you see what has happened here, where I had a lot of negative effects. That was towards the end of September. The factor has taken this very big dip. I multiply this by a value that's very close to 0 for the control unit, so this effect disappears. But if I multiply for some of the treated units, the effect is absorbed by the systematic part. So instead of attributing it to the intervention, it's attributing it to just another temporal trend of the data. So here is I think what's happened here is that my effect modification model is is not correctly specified, you know, and in those examples, it's quite easy for the temporal trends to be confused by causal effects and vice versa, right? And especially when the model for heterogeneity is not correctly specified, this is when the factor loading product will start screaming, yeah, I'm happy to, you know, take whatever residual you cannot accommodate. So we need to find a way to fix that. And so I think you had a talk like some months ago about the cut posterior approach. So this is the approach we're going to take here as well. Nethery and colleagues were the first one who used the cut posterior to sort of, you know, try to prevent this from happening. I think that our computational approach is not quite the same. They make some different assumptions, but that's the idea here. I will solve the problem if I stop the feedback from the treated data Y1 to the parameters of the original model. So the loading, the factors, and the normal variance. And the way I do that is that, you know, by sampling this, which will be the for posterior, I break one of the conditionings. So I estimate theta only solely on the basis of untreated data. So this has been removed. This is the posterior I did for the structure model. I have removed this from the conditioning, and now I'm targeting this new object, yeah? And, you know, the way we simulate from that is very straightforward. I mean, it's not computational Bayesian, but it's already here. You first draw samples from this distribution. For each one of these samples, you do a nested loop and draw samples from the second model. I mean, it's computationally intensive, but not as much as, you know, one would think. This is the hard loop. Once you estimate these parameters, then the inner loop becomes, you know, quite easy to converge, quite easy to compute. So let's do that and see what happens. And this is what I had before. So when I moved from the unstructured model to the structured model, I have this problem. Now with the cut posterior approach, you see that the effects are in much bigger alignment. It's not clear if I've won in, you know, credible interval width. No, not so much, I would say. But what is most important is that I've now managed to, you know, get an estimate of these functions that I was telling you about, like the effect of this calendar time and time of intervention on the magnitude of the effect. And here you can see that, you know, there is a bit of a sign of improvement, yeah? Like start, there is a negative effect. And as we go ahead, people seem to be improving the tracing, right? And this makes sense because the more you are doing the job, the better you get at it. So for calendar time, I don't think I have time, but yeah, I have some guesses about why it looks like that. I'm a bit too late, so I won't have time to discuss it. So just to say that, you know, the cut posterior is, you know, an object that people have started to study a lot recently. I don't think we fully understand its properties. It has some nice properties, and one of these is that, you know, as shown in this paper, that when you have a lot of data, then asymptotically, like, as the number of as your data increases, then the credible intervals that you get for your parameters have, you know, correct frequency coverage. But this is a nice result, but I don't think it applies really to our setting because we are working with finite sample data. So I think there is a bit of a need to further study the properties of this, you know, of this process, understand the theoretical underpinnings. But I think it's quite an active area, so we will have soon more of that. Another thing is that I wanted to say is that also the choice of the cut posterior is not unique, right? Before I prevented my treated data on, you know, giving feedback to the entire parameter vector. Perhaps I could do something in the middle. I could stop them from informing the loadings, but still estimate the factors using, you know, the whole data set. That would stop the problem because it wouldn't be possible, you know, for the data to find the explanation that we found before, right? This leads us to some, you know, objects that are a bit more exotic, let's say, certainly more heavy computational to you know, to fit the data. But, you know, instead of that, we fit this alternative cut posterior that I showed you, we get a much better result. You see, we have reduced the width of the credit interval by a lot with this alternative, and we have much better alignment to the original estimates. But again, this is not an object that we very much understand. So I just wanted to show you some initial results, and we're looking into it further. So I'll start here, just to acknowledge the contribution of my colleagues from the biostatistics unit and from UKHSA. So this is a joint project with the UKHSA. There is a preprint which will appear online soon. Some code. It's being still developed. It's hard to get OpenMP to work with, to make it thread safe. So there will be improvements to that and funding. So yeah, I've said enough. Thank you very much for listening, and happy to take questions.
Thank you for your nice talk. Now I don't know if you have more questions. If we have, I think time for a couple of questions.
Got a question about this introduction of LTP. Currently,
Assalamu alaikum.
stepwise introduced.
Yeah.
So how does that affect your estimation? So for instance, if it had been introduced for all units at the same time, would you still be able to do what you've done?
Yeah.
But then you would extrapolate the first half into the second half, where you don't have any data that you have in the first half.
I still have, I'm requiring at least one control unit. So this control unit will allow me to estimate factors in that second half that you are telling me about. So in principle, I have the data to estimate the factors. The loadings are estimated from the first half. So it is doable, I think. What you want is at least one pre-intervention time point for the units that get the LTP. The more pre-intervention time points you have, the better it is. And you want at least one control unit.
Well, when you get huge uncertainty or something.
Yeah, you certainly get huge uncertainty. That's usually the case. But in principle, you can apply that, and you will get an output. So what kind of output that is?
But then the follow-up question is, would there be some kind of optimal way of introducing this LTP over time? Like, for instance, very quickly at the end or very quickly at the start, or the way it actually moves time?
Yeah. So I think if one had the resources or the ability to do a proper trial, like maybe a stepwise randomized trial, they would know better how to answer this question. I suspect there is an optimal way to, I don't have the knowledge because here everything happened on the basis of interest. One unit would express the interest in the ability to start an LTP, and they would start one. So, and I don't think the results can inform us about, what is the optimal way to, nothing in what I've estimated can tell us about.
Greeting. Assalamu alaikum. May I ask a question, Dr. Nicholas?
Yes.
Doctor, for count time series, integer value time series.
Yeah.
Is there work about that with factor analysis?
Sorry, can you repeat please?
Can you hear us? Can you repeat the question, please? Okay.
What's something about the factor model and count time series?
Okay, well, in any case,
I'm sorry.
you can remain parallel for this. I think We can continue the discussion upstairs, so let's say that again.
I think I have one.
I very happy to run today.